everybody is having a wonderful day today. So back in the barn. Today our lecture, we're moving into chapter 2 and we're looking at 2.1, which is the derivative and slope of a graph. So we're really getting into the calculus today. So this one is a little bit of a longer lecture, okay, because we're learning big things here. So let's get going. So when it comes to calculus, calculus is focused really on one major aspect, and that's a tangent line. So we'll start by defining a tangent line. So a tangent line to a graph is a line that touches the graph at one point. So tangent line touches the graph at just one point. So it's a line that it comes in, skims the graph, and kind of bounces off. So let's say that we had a graph that looked like that, so just a nice polynomial graph. Now, if we were looking at a tangent line here, I first would have to give you a point. So let's say that I said that there's the point we're interested in. Now the tangent line is the line that's going to come down, touch the graph at just that one point, and then continue on its way. Right? So tangent line to the graph. Now, there can be other tangent lines, like we could have a tangent line over here. Oh, let's see where I want this. Let's say we'll have a tangent line right there. And right now, there is the tangent line. Now, eventually this tangent line is going to cross the graph again, but we don't consider that crossing the graph twice because the point that we're interested in is this point here. So even though it is going to cross, we're kind of focusing on what's happening around that point. Okay, so there is another tangent line to this graph. So what I want you to notice is all along the graph, we're going to have different tangent lines. Here's one, here's another one. We could have one going down like this. We could have one going horizontal like this. So there's lots of tangent lines to a graph. And that's what calculus kind of focuses on. So that's what we're looking at. Now the issue is we're looking for slope. Okay? Slope, again, what calculus is all about. But if we want to find the tangent line, the slope of the tangent line, that is going to be a hard thing to do. So finding the slope of a tangent line is hard because we only have one point. Give me 1 second. I'm just going to make sure this is bright enough for you guys. Oh, yeah, this pen works really well. Okay, so slope, remember that we're going to have, if we have 2 points, we can find the slope between them. So if we're looking for slope of a tangent line, the problem is that we only have 1 point. So we're kind of stuck here, right? So instead we're gonna take a step back and we're gonna do this in a different way. So instead of looking at a tangent line, we're gonna look at a secant line instead. So secant lines. And a secant line crosses the graph in 2 points. So again, if we're thinking about slope, if we have 2 points, we can find the slope. Well, a secant line is going to do it for us. So let me go ahead, where's my eraser? Perfect. Okay, let me go ahead and draw another graph and we'll look at a secant line. Ooh. Something to keep in mind, the black does not erase. So let me give you a different graph, a graph that we are familiar with. So to make things easier, we'll just go with our basic parabola here. So we all know that this is x squared. And now what I'm going to do is I'm going to give you 2 points, so there and there, and I will connect between them. Now you got to give my graphs a little bit of a break. I do the best I can, but they're not always perfect. This is actually really, really good for me, so we're doing good so far. So what we have here is a secant line. And the secant line has these 2 points on it, and we can even label these 2 points. I'm going to call this one x sub 1, and this one x sub 2, and this would be y sub 1 and y sub 2. So if we think about it, if we wanted the slope of the secant line, so I'm going to say m secant, then here is where our good old slope formula comes in. So remember, rise over run. So it's going to be y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And as long as we have those 2 points, we can find the equation of that secant line. Okay, now that works well. We found points and slopes of secant lines before. Not a big deal. We've definitely done this before, but that's not what we want. This is not the graph we want. We want a tangent line. So now I'm going to start manipulating this a little bit. So I am going to redraw this graph, hopefully the same graph, but I'm going to relabel it in a different way. Okay, so hopefully this graph looks the same. Trying to draw 2 graphs that are identical is a real challenge. Pretty good. I'm having a good day today. Now, I'm going to start by labeling this one x, but don't get ahead of yourself. We're going to do something different over here. So not x sub 1, but just x there. Now, what I'm going to do is I'm going to label this distance between these 2 hash marks h. So we're going to let the distance be h, which means that this point now becomes x plus h. So if this is x and we add h to it to get over here, so the distance, this becomes x plus h. Everybody okay with that? Now, when we look at that, now using our, oops, that was supposed to be a y sub 2. Using our y sub 1 and our y sub 2 doesn't really make sense to us anymore. So we're going to switch gears and we're going to use our f of x notation. So if this is x, then this is f of x. And if this is x plus h, then this is f of x plus h. So remember, f of x just is another way to write y. So this is like our y sub 1 and our y sub 2, but we're just using this new labeling, okay? So instead of the x1 and x2, we have x and h. So we're changing up our variables just a little bit. And I know at first you might be going like, why do we have to mess with this? This is our slope formula. It's worked for us for years. Why can't we just stick with it? But there is a good reason, I promise. So a little bit of a rework here. Now, when we go to find the slope here, secant, it's still going to be y sub 2 minus y sub 1. It's just that our y's are now in their f of x form. So it's going to look like f of x plus h minus f of x. And then on the bottom, it's still going to be x sub 2 minus x sub 1. But that looks like x plus h minus x. So at first glance, you're like, oh crap, this just looks uglier. But actually, there is some uglier stuff, but there is some simpler stuff. Look at what happens here. The top, you gotta leave it the way it is. But look at what happens on the bottom. So we still have up top f of x plus h minus f of x. But on the bottom, it simplifies to just h. So using this notation, our slope formula, it changes a little bit, but maybe it's a little bit easier because you just have an h in the denominator, okay? Well, it's something you're gonna have to get used to. Whether you like it or not, you gotta get used to it. Okay, so remember that what we've done is instead of labeling the 2 points with different x values, we've labeled the distance between the 2 points. So we have x and then we have x plus h. All right, now I cannot for the life of me figure out what the heck I'm doing. All right, I have this thing in my notes and I really don't want to write it on the board, so we're gonna skip that. Okay, so sorry about that. Now, remember that what we are interested in is what's happening at one point. So we want to get back to that tangent line, not a secant line. So what we're really interested in is a secant or a tangent line where x is. Now right now we have this secant line, but what I want you to think about is if we bring this point, okay, if we bring this point a little bit closer, well, we're still going to have a secant line, aren't we? Okay? If we bring it even a little bit closer, we're still going to have a secant line. But if we can bring that point all the way down to this point, so that the 2 points are laying on top of each other, then will we have a tangent line? But here's the thing. As we bring this point down closer to our original point, this h is going to get smaller and smaller, right? As this comes over here, this distance is going to go this way, and the h is going to get smaller and smaller. Now, eventually, if the 2 points are laying on top of each other, then the h would be 0, wouldn't it? And can we have a 0 in the bottom of a denominator, or in the denominator? We can't, can we? So this is where we've got that issue. Now, I'm hoping that you're noticing something about what we're drawing here. Do you remember when we talked about limits just a couple days ago? Do you remember me drawing those arrows saying we weren't exactly interested what was happening exactly at this point, but what we're interested in is how it approaches that point. So we don't want h to equal exactly 0. If it equals exactly 0, then the 2 points are on top of each other and we can't do this problem. But if h gets closer and closer to 0, bringing the 2 points closer and closer, then things are starting to look good. So that's kind of what we're focusing on here, is that if those 2 points get closer to each other, then we're starting to get closer to a tangent line. So let me change my pen and get back to the right pen there. So again, we're going to say we want a tangent line. So as we said over here, we're going to let h get smaller. To get that tangent line, we're going to bring those 2 points together, which means that h is going to get smaller. Now, if we let h approach 0, is that looking kind of like a limit going on there? Then the slope of the secant line will approach the slope of a tangent line. So what we end up with is m tangent, so not m secant anymore. The slope of a tangent line will be equal to the limit as h approaches 0 of this formula, f of x plus h minus f of x all over h. Okay, so we're using our formula that we found for the secant line, but we're slapping that limit in front of it, and that limit, as we bring that h closer to 0, we're going to bring these 2 points closer together and eventually get to that tangent line and the slope of a tangent line. Okay, now, as we've seen in chapter 1, we can't just plug 0 in here, can we? So this means there's some algebra that we're gonna have to do on these problems, and that's kind of what finding the slope of the tangent line is all about, is the algebra that goes along here. So we are now ready for an example of finding the slope of a tangent line. Okay, so our example says, find the slope of a tangent line to f of x equals x squared plus 1 at the point -1, 2. Okay, so there are a couple of ways to do this, and I could teach you both ways, but after teaching you the first way and then waiting 5 minutes and teaching you the second way, you might be like, why the hell did we do the first way in the first place? So we're just gonna skip the first way, okay? So what we're going to do to find the slope of a tangent line, we're going to take this formula, this f of x, we're gonna leave that on hold for right now. We're gonna take this formula, f of x, and we're gonna find this m tangent. Okay, so we're gonna find the slope of this tangent line, and it's gonna be in this formula form here. So what we need is, we have f of x, we need to find f of x plus h. So before we even get into the formula there, we need to find f of x plus h, which means I need to plug x plus h in there, square it, and add 1. Now, this is a time, like I said, where we're going to use some algebra skills, so we definitely have to FOIL this out. We got to work this out. It's going to get bigger and uglier before it gets simpler and pretty. So if we FOIL this out, so like another x plus h there, we're going to have x squared, then we're going to have 2 x plus h's in the middle, right? xh and another xh. Then we're going to have h squared at the end, and then don't forget the plus 1. So we have the original f of x, and now we have f of x plus h. So now we are ready to plug into the formula. So m tangent is equal to the limit as h approaches 0 of this big guy, x squared plus 2xh plus h squared plus 1, minus the original, so minus x squared plus 1, make sure you put it in the parentheses so the minus distributes, and then this whole thing is going to be over h. Now, there's always going to be some simplification that can go on here, and that's what we're going to do. We're going to do the simplification, but I want to be very clear with you. Every calculus student has to go through this, and even though you might look at the simplification and you might see it really fast, this is a step-by-step process. If you are showing fewer steps than I am showing, you're not showing enough work. So when I ask you to do this on homework or a quiz or whatever, I need to see each step. I need to see each step. Each step had better have the limit on the front of it. This is a process that every calculus student learns, and every calculus student bitches and complains about it, me included. Back when I was learning this, I was like, man, why do we have to do this? So I totally get it, but it's like a rite of passage. We all do it. So, one step at a time. So as we go to simplify this, the limit as h approaches 0, we notice that the x squared minus the x squared will cancel, boop, boop. And also the 1 minus the 1 will cancel. So we have 2xh plus h squared all over h. So it's definitely getting simpler, but we still have this h in the denominator. But if we look up top in our numerator, we notice that both terms have an h in common. So the next step would be to pull out the h. So the limit as h approaches 0 of h times 2x plus h, right? There'll still be an h left there, all over h. But the nice thing about that now is that this h, boop, can cancel with that one. So we have the limit as h approaches 0 of 2x plus h, right? The fraction goes away. And at this point, without a fraction, would it be okay to plug in 0 here? Okay, if we plug in 0 right there, we just end up with 2x. All right, so each step is important. This is like a proof. You're proving to me how this works. So I've got to see all the work, okay, all the work. We only have to do it for like a week and then you can be done with it. But for right now, all the work. Now what we will end up here with is a formula for the slope of the tangent line. Okay, so it doesn't give us the slope of a tangent line, it gives us the formula. But that's where we go back and we get this point. Okay, so we say now, remember that our point was -1, 2. Now if this is the formula, can we plug the x value in there and find what the slope should be? So that's what we're going to do. We're going to say that m tangent is equal to, we'll take this -1 and plug it in there, 2 times -1, which will be -2. So the slope of the tangent line to this graph at this point is -2. So it took us a little bit of work to get there, but we finally got there. Now though, I have another question for you. But now, what if we want the tangent line, the slope of the tangent line, m tangent, for f of x equals x squared plus 1 at the point 2, 5. So we just went through all of this hard work, and then we come over to this problem, and it looks almost the same, except that they give us another point. Now here's the thing, that function is the same as this function here. So do you think all of this work is going to be the same? It is, isn't it? So does that mean we have to redo it? No, okay, don't redo that again. Do we know what the formula for the tangent line was? If this is our function, the formula for m tangent is 2x. That is not going to change from this problem to this problem. What is going to change is that over here, we plugged in -1 because that was our x value. What are we going to plug in over here? This time our x value is 2, so that's going to come down here, and we'll say that the m tangent, slope of the tangent line, is 2 times 2, which is 4. So at this first point, -1, 2, the slope of the tangent line was -2, but over at this point, the slope of the tangent line is 4. But we didn't have to do all the hard work again. So do you see how by doing this work one time, proving to me that this is how it works, you can then use those results over here, and then any point that I give you, you can just use the results. Use the results. See how that works? Okay, so let's do a couple more of these. We're just going to get used to this process. Okay, used to this process. So this says find m tangent for f of x equals 2x plus 5. Now again, I'm going to say I know there are some of you that know ahead of time what the answer is going to be because either you've taken calculus before or you figured this out. There's a pattern that goes on here. But for this lecture and for this homework, you're doing it out the long way, even if you know what the answer is. I know what the answer is. I still do it out the long way because that's what we're doing in this section, okay? So this time they didn't give us a point. They just want the formula or m tangent. So I know I erased it, it was over here before, but we need f of x, which we have, but we also need f of x plus h. So we're going to find f of x plus h. by plugging in x plus h right there, and then multiplying out 2x plus 2h plus 5. So to find the slope of the tangent line, we're going to say let the limit as h approaches 0, okay, have that. And now, I know I erased it, so hopefully you got it there. It's this guy minus that guy. So it's going to be 2x plus 2h plus 5 minus 2x plus 5 in parentheses, all divided by h. Now remember what we said, there should always be some simplifying that goes on. So when you look at this one, the 2x minus 2x will go, yes? And the 5 minus the 5 will go. So what we're still left with is a 2h up top and an h on the bottom. But lucky for us, those h's cancel, so we're left with the limit as h approaches 0 of 2. Okay? And we know that the limit as h approaches 0 of 2 isn't going to change, right? There's no 0 to plug in there. So the answer here is strictly 2. So for this equation, it actually doesn't matter what the point is. This guy is always going to have a slope of 2. Okay? The tangent line will always be 2. And what I want you to do is look at that guy back up there, 2x plus 5. Isn't that already a line? So a tangent line doesn't really make sense in this one. This is already a line, so the slope of the line is 2. We're done. Okay. But there it is with the work shown out, and we do get the answer 2. So it did work exactly how it's supposed to. Now, this little process that we've done twice, and we're going to do it a couple more times here, this M tangent. Another way of talking about this, instead of me continuing to say M tangent, is to call this what it's called, and that is the derivative. What we're finding here is the derivative. So the derivative of f at x is, and we're going to stop using this notation, so the M tangent we're going to let go, and we're going to use a new notation that looks like this. F prime of x, and that's how you say that, F prime. It's not a 1, it's like an apostrophe. So F prime of x, and then F prime of x is just the formula we've just been using, the limit as h approaches 0 of f of x plus h minus f of x all over h. So it was M tangent a minute ago. Now it's the same formula, but it's got its new notation. It's got its function notation, f prime of x. So this is the derivative of x, which is the which is the slope of the tangent line. Okay, so the same thing going on here. Now, there are a couple different notations that we do use for this. So the most common, again, is this f prime of x, but sometimes we will also see it as y prime. Okay. Another way to see it will be dy over dx. Okay, dy dx means the change in y over the change in x, so that's kind of the slope formula there. Or the last way we sometimes see this is d dx f of x. Okay. And that does pop up every once in a while, but these three are kind of our main go-tos, right? But yes, we will definitely use those different notations. And if you want to go back and use M tangent to start with, if you're feeling more comfortable with that, go for it. But eventually you're going to make the switch, and we'll almost always use one of these two guys. Okay, so the only thing that's changed there is the notation, otherwise the process is the same. So this time, instead of me saying find M tangent for a function, I can say find the derivative of f of x equals x squared plus 5x. So find the derivative just means the same thing. It means find m tangent, find that like formula for the tangent line. So we're doing the same thing, we're just giving it a different name out front. But we need f of x plus h, we already have the f of x. So let's find f of x plus h, where we're gonna plug x plus h there, square it, and then we're gonna plug it, don't forget it has to go here as well, right? It's gotta go in both of them. So when we multiply out and we FOIL this guy out, this is gonna be x squared plus 2xh plus h squared plus 5x plus 5h. Right? We distribute in there as well. Okay, so now we're ready to say the derivative of x, f prime of x, is equal to this guy minus that guy. So x squared plus 2xh plus h squared plus 5x plus 5h minus, parentheses, x squared plus 5x. All over h. And look at what I forgot, because I got so excited, I forgot the most important part, the limit as h approaches 0. So see, it's easy to forget it, but don't forget it, okay? It's important. That h approaches 0 part is very important for doing this. Okay, so even if you get excited. All right, now again, things should cancel. So we've got an x squared here minus x squared there. And we have a 5x here minus 5x there. So then we're left with the limit as h approaches 0 of 2xh plus h squared plus 5h, right? That's what's left up top, all over h. But the nice thing about this is that they all have an h in common, yes? So we'll say the limit as h approaches 0 of h times 2x plus h plus 5, right, if we pull out an h, all over h. Okay. And that allows us to cancel out the h's. So one more time here, the limit as h approaches 0 of 2x plus h plus 5. And now with the fraction gone, we can actually plug in the 0 there, and we end up with 2x plus 5, right? That goes away. So we say the derivative is 2x plus 5. Now remember, this is just a derivative formula, okay? The derivative is just another formula. So we've taken the original function and we found the function of its slope. Okay, so this is the slope function for that original function. And we note that they're related. That guy's f of x and this guy's f prime of x. Okay, so how about a different looking guy altogether? So this time we're going to find the derivative. For f of t equals 2 over t. Okay. So in this one, they are doing two things to you. First off, they've changed the variable on us from x to t. And this is important because there are a number of times where we're going to see t standing for time normally. So in applications, there's a lot of time problems that we end up doing. So t is one thing. The other thing is, it's a fraction. So we got two different things going on than we've seen in the last couple examples. Well, we can do it. We can still figure it out. So we have the original but what we need as well is f of t plus h, which means I'm just going to put a t plus h in the denominator. Okay, so now, remember this is f prime of t, okay, so I know it's easy to get caught up and put the x back in there, f prime of t. So we're going to go this guy minus that guy. So we're going to go 2 over t plus h minus 2 over t, all over h. So what we end up, look what I did again. Look what I did again. I get so excited that I forget the limit as h approaches 0. Not showing good technique today. Okay, get all excited. Don't forget your limit sign. Okay, now up top here, okay, we've got a rational equation, and then there's in another rational equation. So we've got a big old complex fraction going on here. Now, if we were to subtract these two guys up top, in order to do that, we would need a common denominator, wouldn't we? So the denominator here is a t plus h, and this denominator is a t. So we're going to need to combine them to get our common denominator, right? Which means this guy is going to need a t, which means this guy up here is going to need a t, and this guy is going to need a t plus h, which means this guy is going to need a t plus h. Everybody agree? Right? Common denominator going on there. So we'll say the limit as h approaches 0. So now we'll have 2t minus, and then we're going to have 2t minus h. Everybody see that up top there? But this is all going to be over t times t plus h. Okay, everybody see the 2t, and then 2t plus, forgot the 2h. It's not a good day apparently. Sometimes you have these days, sometimes you don't. Okay, look better? Hopefully that looks better. All right, okay. All over the h that's on the bottom. Okay, so still some simplifying to do on the top. So we'll say the limit as h approaches 0. Luckily, boop, boop. So we still have minus 2h over t plus h all over h. Okay, now you got to remember what to do when there's a complex fraction. So remember that this guy is like h over 1, right? So when you have a complex fraction, could we take this bottom guy and flip and multiply? So could we write this as the limit as h approaches 0 of negative 2h over t plus h times 1 over h. Okay, wouldn't that be another way to write that if we flip and multiply? And the nice thing about that is, boop, boop. So one more time here, the limit as h approaches 0. And now up top we have negative 2 over t plus h. Now there still is an h in the denominator, isn't there? But the thing with this h in the denominator is if we plug in 0 there, that's just going to disappear. Does the bottom of the fraction become 0? It doesn't, does it? So if we plug in 0 there, we end up with negative 2 over t squared. So we found that the derivative is negative 2 over t squared. So again, another little formula there going on. Right? And in that one, we had to use a lot of algebra skills. So, we used canceling, we used common denominators, we used complex fractions. So a lot of stuff went on in there. But by working through the algebra skills, we were able to get finally to something that we could simplify. Okay, now, after all of that work, what if I then said, now of a tangent line through the point 1, 2. So this leads us to where we're headed. We're back to that tangent line. Now remember, this derivative formula here that they've given us, this is the slope of the tangent line. Now if we want the equation of the tangent line, don't we need the slope and a point? Okay, we need both of those, a slope and a point. Well, if we can find the slope, we've got our point, we're good to go. Now, again, they made this one a little bit uglier in that this is ty, not xy, but it still works the same way. So we're gonna plug in that first coordinate into our slope there. So we're gonna say the slope of the tangent line, the derivative, is gonna be -2 over 1 squared, which just gives us -2, right? Okay. So then we're going to go to our equation, the y minus y sub 1 equation equals m times, in this case it's going to be t minus t sub 1. I'll write it out here for us. T minus t sub 1. Okay, so instead of the x and y, we've got t's in there, but that's okay, we can deal with that. Okay, so we're going to plug in our y. So y minus 2 equals our m, -2, and then t minus our 1. So y minus 2 equals -2t plus 2. Then we'll add the 2 more. So we got y equals -2t plus 4. So not only did we find the slope of our tangent line, -2, but we actually found the tangent line itself. Okay? The tangent line itself is -2t plus 4. All right, look good? Okay. So that's the process, that's what you're looking at. So now if it asked you just to find the derivative, just finding the derivative is finding this guy. If it asks you to find the slope, finding the slope is just this guy. Or it could ask you to go the whole way and find the tangent line, which means you got to do the whole entire thing. So when it says find the equation of a tangent line, that one you know you're going through the whole entire process, which can be a little bit tedious, but you can do it. Okay, we've seen it again. Now remember, all of those steps are important. If I ask you to do this in your homework, I need to see all of those steps. And a lot of times I'll write in there, make sure to use the long way. Make sure to use the derivative formula so that you know that I want you to show each step. Okay, now a teeny bit more and then we're done. Oh, wait a minute. Yeah, just one page left. So we've got a little theorem that goes along with this. So this says, if a function is differentiable, then it is continuous. So remember that in the last section, we were looking at continuity or discontinuity. So differentiable means that we can find the derivative. We can do what we did. So this says if you can find the derivative, if a function is differentiable, then it is continuous. So if we're looking at a function and we're trying to find the slope of the tangent line and you can actually do it, it means that the original function was continuous, which should make sense. Now, the thing about this is not actually what it says right here, is the flip. So this is not true the other way. So not the other way. So what I mean there is if a function is continuous, it's not necessarily differentiable. So just because a function is continuous doesn't mean you can take the derivative. And so that leads us to exceptions for taking the derivative. So I want to give you an example here. So here's an example of a function that we have all seen before. If you don't remember, this guy is the absolute value of x. Now remember that derivative means the slope of the tangent line. So any point on here needs to have a tangent line, and it does here and here. But what I want you to notice is if I ask you for this point right there, what does the tangent line look like there? So look at this. Could this be a tangent line at that point? Is it touching at only one point? Could this guy be a tangent line at that point? Could this guy be a tangent line at that point? So because the absolute value comes down to a point like that, the tangent line at that point could be any different slope, right? It could wobble back and forth there. So this is an example where the graph itself was continuous, but at this point right here, there is no derivative. So no derivative at x equals 0. And we call this a node or a cusp, okay? And the reason why is obviously what we just said is they come to a point, but in the words of math, point has another meaning, right? That's a point. So to say point there is kind of like, wait a minute, what do you mean that comes to a point? So we call this a node or a cusp instead. So what this little theorem and then this idea leads us to is that a function is not differentiable at x when there is either a discontinuity a vertical asymptote, or wait a minute, a vertical tangent, not asymptote, got carried away there, a vertical tangent, or third, a node, or a cusp. So we can take the derivative almost everywhere, okay? The derivative is almost always good except at these particular situations. So a discontinuity, okay, so if there's a hole in the graph or a jump in the graph, we cannot take the derivative. A vertical tangent. Now in this example, a vertical tangent, let's say we had a graph that looked like this. So the idea is right about here, okay, again, give my graph a little bit of leeway there. There is a tangent line, but the tangent line actually comes down straight up and down through that point. And so it's a vertical line. But what I want you to think about is, what is the slope of a vertical line? Right? And this guy has no slope, does it? So if there's no slope, and derivative means slope, then that means there's no derivative. So every once in a while, it's very rare that this happens, but every once in a while we end up with a vertical tangent, and then that is not differentiable. So we've got the discontinuity, a vertical tangent where there's no slope, and then the last example is where there's a node or a cusp. So almost everywhere else, you can take the derivative except if you have one of those three situations. Okey-dokey. Okay, so for homework then tonight, you are working with finding the derivative using the limit as h approaches 0 of f of x plus h minus f of x all over h, using that notation, and working through each problem all the way out. And then Once you've done that a number of times and you're feeling firm with that, then we'll move on to the next section where we'll learn a couple shortcuts. Okay? Alrighty, have a good day.